I gave a theorem in which we said that even if it is not completely increasing or decreasing, that means there can be multiple images. Then also you can find out the distribution by dividing into the regions in which the function is either increasing or decreasing. Calculate the density in each region and then sum them up. So I will give one example of that. So suppose x follows normal 0, 1. So what is the density function of x? That is 1 by root 2 pi e to the power minus x square by 2. Now I have y is equal to x square. So I have here, this is, you can see that it is decreasing and then increasing, isn't it? Two inverses will be there. So you have x is equal to minus root y and x is equal to plus root y. So we will calculate the dg inverse y by dy in both the regions, that is dx by dy, that is equal to minus 1 by 2 root y. And here it will be dx by dy is equal to 1 by 2 root y. So you have to take, of course, mod here. So dx by dy is equal to 1 by 2 root y in both parts. Okay. So what is the distribution of so the PDF of y fyy, that is equal to, in the first region, 1 by root 2 pi e to the power minus y by 2, 1 by 2 root y plus 1 by root 2 pi e to the power minus y by 2, 1 by 2 root y. So this you can combine, it will become 1 by root 2 pi y e to the power minus y by 2. Of course, this is for y greater than 0. For y less than 0, this will become 0 because there is no inverse for y less than 0. Of course, equal to 0 you can include either here or here, it will not make any difference because it is a continuous distribution. Is that okay? Do you follow this calculation? If x follows normal 0, 1, then y, that is x square, it follows this distribution. And in fact, you can identify this. It is what? 1 by 2 to the power half gamma half y to the power 1 by 2 minus 1 e to the power minus y by 2, which is nothing but a gamma distribution with half, r is equal to half and lambda is also half. Okay. Which I already mentioned to you that the distributions in the continuous cases, they are all connected. I gave you one result, that is the probability integral transform. Is it okay? This example is clear? Sir. Okay. Now I move to another topic. We go to the several random variables. Okay, that is called jointly distributed random variables. So far the discussion that I gave, that given a random experiment we define, so we have one sample space and from that one sample space we consider one random variable. Okay, so for example it could be blood pressure of a patient, it could be marks of the student in a test. It could be height of the person. It could be income of a employee and so on. However, many times what happens that we are making several measurements on the same object. In the same random experiment, there are several things are done. So for example, if somebody falls sick and he goes to a clinic, then they will measure his not only his temperature, they will measure his weight, they will measure his blood pressure, they may measure say oxygen level and so on, isn't it? So that means in place of one, see, it could be X1 could be body temperature, X2 could be say oxygen level. Nowadays, if you get a fever and you go to hospital, they will check oxygen level all the time. And then of course, your systolic blood pressure, X4 could be diastolic blood pressure, and maybe X5, they will take the pulse rate and so on. So for the same patient, you have now 5 observations, not one observation. And of course, each of them will vary depending upon their ranges, whatever is there. For example, blood pressure is measured in certain numbers, like you say 120 by 80, like systolic and diastolic. So the upper one ranges from say 110 to 140, and the lower one ranges from say 60 to 90 and so on. Similarly, the pulse rate, it may vary from say 65 to 110 or something like that. Oxygen level can be between 90 to 100, and if it is poor, then of course it can be much less also. Similarly, the ranges of, but overall what we are saying is that it has a distribution. Similarly, you can have say your X1 could be marks in course 1. Okay, you are doing say maybe 5 courses in a semester. So your marks or grades, for example, marks in course 2 and so on. Okay, say X6 is say marks in course 6. So the random variable here will denote for a particular student X1, X2, X6. So in general, you have X is equal to X1, X2, Xk. That is a function from omega to k dimensional Euclidean space. Okay, so this is a k dimensional random variable. Now, when you have one random variable, you have discussed the concept of cumulative distribution, you have discussed the concept of probability mass function, that is the discrete random variable, and you have discussed the concept of probability density function for a continuous random variable. So similarly, when you discuss multi-random variable or a jointly distributed random variable, which we of course we can call it a random vector, okay, it has become a random vector, then also you have the similar concepts. That means you may have all of them to be discrete, all of them to be continuous, some of them may be discrete and some of them may be continuous and so on. All kind of possibilities are there. So we can consider, for example, firstly let us take up the cumulative distribution function. Okay, CDF of a random vector. So you can consider say f of x, that is the probability of x1 less than or equal to x1 and so on, xk less than or equal to xk. For convenience of teaching, let me take up the case of two-dimensional first, and then we will extend the ideas to k dimension. For explanation purpose, let us consider, let us first take the case k equal to 2. Okay. So if I take the case k equal to 2, let us consider say x, y. Okay. It is easy to talk about rather than x1, x2. So x, y, they will take values over certain region x cross y. Okay. And let us consider say f x y, the joint CDF. This is nothing but probability of x less than or equal to x and y less than or equal to y. Okay, for all x, y belonging to R2. Like the case of one dimension, you had certain properties for the CDF. Okay, now this is a function of two variables, so you can look at the properties. See, in the case of one variable, when x was going to minus infinity, fx was going to 0. Now, if you are dealing with the two-dimensional thing, then also the similar thing will happen. So you will have the following properties, which of course you can verify very easily. First is that if I take limit of fxy as say x tends to minus infinity, this is going to be 0. And of course, if you take as y tends to minus infinity, then also this is going to be 0. The reason is that if I take x tending to minus infinity or y tending to minus infinity, it corresponds to an empty set, and therefore this is going to become 0. Similarly, if I take limit of fxy as say x tends to plus infinity. If I take x tends to plus infinity, then for x the entire region has been taken. So this will reduce to probability of y less than or equal to y. That is nothing but the CDF of y. So if I take limit as x tends to infinity, I get the CDF of y. And if I take the limit as y tending to infinity, I will get the CDF of x. Then f is non-decreasing in each of its arguments. Then f is continuous from right in each of the arguments. So these are some of the basic properties of the joint cumulative distribution function of two random variables x and y. Okay. So is it clear?
Yes, sir.
Now let us consider the case when all of them can be discrete. Then you can have a joint probability mass function, and all of them are continuous. Then you can have a joint probability density function. So these two special cases let us consider. Of course, you can have various complex situations also, that x can be discrete, y can be continuous, and so on. So of course, for that purpose, the joint distribution function or the joint cumulative distribution function is good for describing the distribution. Okay, so let us consider discrete case. Suppose both x and y are discrete. So then we are having the joint probability mass function. Probability of x is equal to xi, y is equal to yj. That is pxy, xi, yj. As in the case of one variable, because there we had probability of x is equal to xi as equal to pxi. Then you can consider that these probabilities are non-negative, of course, which is true. And the sum over all the possible values is equal to 1. So let me explain through one example here. Suppose there are say 10 computers, okay, in a say a showroom, okay, and out of that suppose 5 are good, okay, and say 2 have say defective monitor, and say 3 have say defective CPU, okay, some defect in the CPU. So suppose 2 computers are selected at random, and I define x is the number of computers with defective monitor, and y is the number of computers with say defective CPU. Okay, so I just put DMDC. What is the probability distribution of xy? Okay. So that is Pxy, the probability x is equal to 0, y is equal to 0. It means that both computers are good ones, so that is 5C2 divided by 10C2. So of course you can simplify this. It becomes basically Let me just write it in common denominator so that it will be easy for us to verify. It is 2 by 9, but I am writing it as 10 by 45. Okay. Then let us look at, say, what is the probability that x is equal to 0, y is equal to 1. So that means 1 is good and 1 is selected with defective CPU. And how many of them were with defective CPU? We had 3 with defective CPU. So this is 3C1 divided by 10C2. So it is 1 by 3. Of course, I will write it as 15 by 45. Okay. So similarly, you can calculate the probabilities for 1, 0, 1, 1, 1, 2, and so on. So all the things can be calculated. So the PMF can be represented so let us put it in the tabular form because it is a finite number of values and few values are there, so we can nicely put it in that form. So x can take values 0, 1, 2, y can take values 0, 1, and 2. We calculated PXY00 as 10 by 45, 01 as 15 by 45. We can calculate 02 also. So 02 is also similarly, it will be 3C2 divided by 10C2. So that is becoming 3 by 45. Then 10 will become 2 C1 and then this one. So that will give you into 5C2. So that is 10 by 45. Then 1 will become 2C1, 3C1. So that is 6 by 45. 1, 2 will become 0 because total we are selecting only 2. So we cannot have 1, 2. 2, 0 will become then of course 2C2, that is 1. So 1 by 45. And then 2, 1 and 2, 2 are not possible. So this is the joint probability distribution of XY. Okay. From here we can evaluate any probability which we require. For example, if I want to ask what is the probability that x is less than or equal to 1, y less than or equal to 1, then it means you are calculating probability of xy is equal to 0, 0, probability xy is equal to 0, 1, probability xy is equal to 1, 0, and probability of xy is equal to 1, 1. So this is equal to 10 by 45 plus 15 by 45 plus 10 by 45 plus 6 by 45. So that is equal to 41 by 40. So you can calculate any probabilities related to the joint distribution. Is it clear? Well, is this example clear?
Yes, sir.
Now you can see some more things here. Suppose I add all the probabilities related to, say, x is equal to 0. That means x equal to 0, y is equal to 0, x equal to 0, y is equal to 1, x equal to 0, y is equal to 2. If I do that, then I will get, so this will become basically probability that x is equal to 0. So actually the marginal distribution of x can be obtained if I sum over all the values of y. So similarly, if I want to calculate what is the probability x equal to 1, then that will become 21 by 45. Sorry, this is 16. And what is the probability x equal to 2? That will become 1 by 45. So summing over all the values of y, we get the probability distribution of x. This is called marginal distribution of x. Okay. Marginal PMF of x. Similarly, if I sum over values of x, I will get the marginal distribution of y. So for example, this will become 21 by 45, 21 by 45 and 3 by 45. This is the marginal PMF of y. So from a joint distribution, we can calculate the individual distributions of the involved random variables. So the general definition would be, so marginal PMF of x is Pxxi, that is obtained by considering the sum over all the values of y of the joint probability mass function. Similarly, the marginal PMF of x of y that is summation Pxy xiyj xi belonging to x. From here, you can also consider conditional probabilities. What is the meaning of conditional probabilities? We can consider the conditional probability mass function of x given that y is equal to yj. So that is, we will use the notation like this. That is probability of x is equal to xi given y is equal to yj. So if you apply the definition of the conditional probability, that is probability of A given B is probability of A intersection B divided by probability of B, then this becomes nothing but the joint probability mass function of xy divided by the marginal distribution of this. Similarly, you can calculate the conditional probability mass function of y given x is equal to xi. So that is equal to Pxy. So this is basically probability of y is equal to yj given x is equal to xi. So once again, if I apply the definition of the conditional probability, it becomes the joint at xi yj divided by the marginal distribution of xi. So for example, in the earlier thing that we have done, suppose I want to find out the conditional PMF of y given say x is equal to 0. Okay. If you want to find out this, then I have to consider say for example, or we can put here 0 given 0. So that is Pxy 0 0 divided by probability that x is equal to 0. So these values we have already calculated. It is 10 by 45 and this one was 28 by 45. So this becomes 10 by 28. Similarly, if I consider what is the probability y is equal to 1, then given that x equal to 0, that will become P xy 0 1 divided by P, that is 15 by 45 divided by 28 by 45. So that will become 15 by 28. And the probability of y is equal to 2 given that x equal to 0, that is Pxy 0 2 divided by Px0, that will become 3 by 45 divided by 28 by 45, that is 3 by 28. You can easily see that this is a valid distribution, 10 by 28 plus 15 by 28 plus 3 by 28, the sum is equal to 1. Is this clear?
Yes, sir.
Yes, sir. Yes, sir.
So I have discussed the case of discrete jointly distributed random variables. We have a joint probability mass function. From there we can calculate the marginal distributions. That means individual distributions of x and y can be calculated from there. We can also find out the conditional distributions of x given y and y given x from there. Now let us move to the continuous case. If both the random variables are continuous, so we call it a jointly continuous random variable. Let xy be jointly distributed continuous. So we will have joint probability density function. Okay. So then what will be the properties here? As you remember, in the case of one variable, the density does not denote the probability at the point, it denotes the density. So what are the conditions that you have? That this function should be non-negative, for all xy. Okay, density function is a non-negative function. Second is that the integral over the whole domain must be equal to 1. Of course, this integration can be done in any order, like I am writing dx dy, but if I write dy dx, then also this should be same. Okay. Both should be 1. Okay. Both are equal. And the third property in the case of one variable was that if we consider the probability of any set on the real line, then the probability of that set is nothing but the integral of the density function over that set. So the same thing is true in the case of this also. For any measurable set B in the two-dimensional space, probability that xy belongs to B is nothing but integral over B of the density function. And once again, I mean, the order is immaterial. You can have dy dx also. As in the case of one variable, we can calculate the marginal distributions and we can define the conditional distributions. So the marginal PDF of x is if you integrate with respect to x, then you will get the marginal of y. You can also calculate the conditional densities, conditional PDF of x given y is equal to y, that is defined as fx given y is equal to y, that is the joint of x and y divided by the marginal distribution of y. And similarly, the conditional distribution of y given x So let us take some example here. Let us consider, let x, y be jointly continuous with the probability density function given by, say, 10xy square Okay, if x is less than y and they lie in the interval 0 to 1, then the density function is 10xy square, otherwise it is 0. Okay, basically the density has been defined in this portion. If I consider, say, two-dimensional space and I consider this point, so x less than y, that is this region, this is the region of the density. Let us look at here various things here. For example, I want to find out the marginal distribution. So what are the marginal distributions of x and y, etc. So the marginal PDF of x. So it is obtained by integrating the joint PDF with respect to y over the given region. So what is the range of y? Y is from x to 1. Okay. So if I integrate this, y cube by 3 I will get. So it will become 10 by 3 x into 1 minus x cube. Okay. So this is the probability density function of x alone. Is this calculation clear?
Yes, sir.
In a similar way, you can calculate the probability density function of y also. So then you will integrate with respect to x. So 10xy square dx, and the region of x is 0 to y. So that gives us x square by 2, so y square. So 5y to the power 4. So this is the marginal probability density function of y. Is that okay?
Yes, sir. Yes.
So first thing is that you can calculate various probabilities related to x and y and jointly of x and y. So let us just take up some small exercises here. Suppose I ask the question, what is the probability? Okay, say probability x less than 1 by 4. Then this will be calculated from the density function of x integrated from 0 to 1 by 4. So that is 10 by 3 x into 1 minus x cube dx 0 to 1 by 4. Okay. So of course this can be easily evaluated, 10 by 3 and then you have x square by 2, so that becomes 1 by 16, 1 by 32, and here you will get x to the power 4, so that is x to the power 5 by 5, so 1 by 5 and 4 to the power 5. So this of course you can evaluate easily. than say 3 by 4. That's the dy from 3 by 4. So that is y to the power 5. That is 1 minus 3 by 4 to the power 5. Okay. We can calculate joint probabilities also. Suppose I ask you, what is the probability of say x plus y less than half? Integrate the density over this region. See, what is the region here? See, x less than y. This is the region of the density. Okay. So, in that region, here I put x plus y less than half. So, what will be that? This will be this region. This is x plus y is equal to half, say. So, this is half 0. This is 0 half. This will be 1 by 4, 1 by 4. The density is in this part, so I will have effectively only this region. Okay, only this region will come. So this is integral of the density 10xy square, and you can again do either dx dy or dy dx. So let us put say dy dx x 0 less than x plus y less than half. This is the region. 10xy square. Suppose I integrate with respect to y first. So y is from this line to this line, that is x to this line is x plus y is equal to half. So this will become half minus x, and then x is from 0 to 1 by 4 dy dx. Is this region clear to you, the region of integration?
Yes, sir.
So this becomes then 10 by 3, 0 to 1 by 4. So y cube, that is half minus x cube minus x cube, and of course it is multiplied by x. Okay. And in the next step you can get the answer. So I am not writing down the full calculation here. You can do it. Suppose I give another joint probability calculation. Suppose I say, what is the probability that x is between 0 and say half, and y is between say 1 by 4 and 3 by 4. Okay. So again you draw the region here, because you have to determine the region of integration. This is the actually region x less than y, because your density is in this part. Now if I say 0 less than x less than half, then you are here. So for x 0 to half, and then for y it is 1 by 4 to 3 by 4. So I draw this line, that is 1 by 4 and this is 3 by 4. So y is in this region and x is in this region. So basically this is the region now coming in. Okay. So you can see here the region of integration. If I split like this, I can get two parts here. Firstly, if I do with respect to x or with respect to y, accordingly we can determine. Okay, so either I can cut like this or I can cut like this. So let me do it like this. Okay. So this becomes 10xy square, and if I can do dx dy here, so then x is from 0 to 1/4 and y is from 1/4 to 3/4. That is this part. Okay, this particular part. And then if I look at this part, then in this part y is from x to 3/4 and x is from 1/4 to 1/2. Is this description of the region understandable to you?
Yes, sir.
Now, in a similar way, we can calculate the conditional distributions also here. We have calculated the marginals, we can calculate the conditionals also here. So, for example, if I ask so this calculation you can do, I mean, just it's a matter of integration, so I will not write the calculation. The conditional probability density function of x given y. So that is the joint distribution here of xy given y. So joint is 10xy square divided by 5y to the power 4. So that will become 2 x, so x, then y to the power 4. So okay, that will become y square in the denominator. For a value of y fixed between 0 to 1, x lies from 0 to y and it is 0 elsewhere. So this is the conditional probability distribution of x given y. Okay. Similarly, the conditional PDF of y given x. Again, that is 10 by 3, so that will become 3, and then x will get cancelled out, so you will get 3y square divided by 1 minus x cube, where y will lie between x and 1, where of course x is a number between 0 and 1. So this is the probability density function of y given x. Once again, you can calculate conditional probabilities also from here. So suppose I want to calculate say probability of x less than half given y is equal to 3/4. Okay. So this will be calculated from the conditional distribution of x given y is equal to 3/4. So you can write down here. Yeah. So find out the conditional distribution of x given y is equal to 3/4. So I have written the general expression of x given y is equal to y. Here you put y is equal to 3/4. So that will become 9/16. So that is becoming 32/9. So this distribution then becomes 32 by 9x for x lying between 0 to 3 by 4. So from here, if I calculate this probability, then I have to integrate only this 32 by 9x from 0 to 3 by 4. 0 to 1 by 2 because x is less than half. So this integral, of course, you can easily evaluate. Is it clear?
Yes, sir.
Similarly, suppose I want to find out another probability, say y less than half given x is equal to say 1 by 4. Okay. So again, I will need the conditional distribution of y given x is equal to 1 by 4. So we have calculated the conditional distribution of y given x. The general form I have written y given x. This is the form. Here you put x equal to 1 by 4. If you put that, you will get, so f y given x is equal to 1 by 4. So that is becoming then 64 by 21 y square for 1 by 4 less than y less than 1, and it is 0 elsewhere. So then you consider probability y less than half given x is equal to 1 by 4. So that is integral of 64 by 21 y square from 1 by 4 to 1 by 2 dy. Of course, you can easily evaluate it. It is 1 by 9. So I hope the calculations are clear to you.
Yes, sir.
So we can break for 5 minutes and then we will start the joint movements and other things. Okay, so I will talk about it. So let us take a break for 5 minutes. Next we talk about the, like when we consider the joint probability, then we talk about the independence of the events. Similarly, when we talk about the jointly distributed random variables, we can talk about the independence of the random variables. So we say that random variables x and y are independent. Random variables x and y are independently distributed. If the joint CDF will be equal to the product of the So if we consider the discrete and continuous cases separately, then it will become that the joint PMF is equal to the product of marginal PMFs, and the joint PDF is equal to the product of marginal PDFs. In case x, y are discrete, the condition can be written as Pxy is equal to Pxxi Pyyj for all xi yj. Similarly, in case both are continuous, the condition can be that the joint probability density function is equal to the product of the marginal probability density functions. Of course, I mean this condition does not mean that we have to only verify that the random variables are independent. It is for the practical applications that when we are having independent experiments, so out of the independent experiments, independent random variables will arise, and now we need to combine the results of our outcomes of those experiments. So if that happens, then we can just multiply out and use that thing. So that is the main purpose of having independent random variables. Of course, it is not just for the technical purpose that we just check the conditions or something like that. Okay. So let me just give you one or two very simple examples. So let us take a discrete case, say probability of that is equal to say 1/4. 1, 0 is 1/4. 0 is 1/4, and that is 1, 1, that is also 1/4. So if I calculate the marginal distribution, Px0 is half, Px1 is half, and similarly if I consider Py0, that is half, and Py1 is half. So you can easily then check that is equal to the product for all the conditions. Okay, for all values of x and y, this will be true. So here x and y are independently distributed random variables. Let us take another example of the continuous case. Suppose I say this is say e to the power minus 2y, and I put 0 less than x less than 2 and y greater than 0. Okay. Then what are the marginal distributions? For example, what is the marginal distribution of x here? You integrate e to the power minus 2y dy 0 to infinity. So you will get half here. Similarly, if you calculate the marginal distribution of x y, then you will integrate with respect to x from 0 to 2 e to the power minus 2y dx. So that you will get 2 e to the power minus 2y for y greater than 0. So again you can see that the product of fx fy gives you fxy. So you can see that x and y are independently distributed here. Are these examples clear? Is this concept clear of independence of random variables?
Yes, sir.
Now I talk about the joint moments. Okay, so we have the concept of expectation in the case of one variable. We defined expectation of gx as sigma of gxi probability of x equal to xi or integral gx fx dx. Similarly, when we have two variables, we can talk about the expectation of the function of two variables. Okay, so joint expectation. Okay. So if I have g a function of xy, okay, so we consider expectation of gxy. If both x and y are discrete, then this will become double summation g of xi yj the sum is over all xi yj, and if it is continuous, then it will become of course this dx dy can be dy dx also. Okay, you can write any of them, both are same. because the reason is that if the expectation exists, then both will be same, and if the expectation does not exist, then of course they will not be the same, but then that case we are not considering. Okay, because we are considering provided the series or the integral on the right are absolutely convergent. Okay, so this is the discrete case and this is the continuous case. So then we can talk about the product moments. So RSth non-central product moment, let me use the notation RS, okay, prime, mu prime RS, that is expectation of x to the power R, y to the power S, okay. RSth non-central product moment. And in particular, see, if I consider here R is equal to 1, S is equal to 0, I will get expectation x. Similarly, if I put R is equal to 0, S is equal to 1, I will get expectation y. Okay, so they are the special cases. Okay, so that is mu1 0 prime, that is expectation of x. We generally write it as mu x also, and mu 0 1 prime, that is expectation of y, and we also have mu 1 1 prime, that is the first product moment, expectation xy. We sometimes write it as mu xy. Okay, like in the case of one variable, we can also define central product moments also. So are these definitions clear?
Yes, sir.
Mu rs, that is expectation of x minus mu x to the power r into y minus mu y to the power s. So this is rsth central product moment. Mu 1 1 is equal to expectation of x minus mu x, y minus mu y. This is called covariance between x and y. Okay, so the first central product moment, that is called the covariance between x and y. Why the name covariance? If you remember, expectation of x minus mu x square, that was the variance, so that will be variance of x. If I consider expectation of y minus mu y square, that will become the variance of y. That means what is the variability of x with respect to its mean? what is the variability of y with respect to its mean. So now if I am considering x minus mu x into y minus mu y, it means what is the relative variation of x with respect to y. That means whether f x more values of x are bigger than mu x, whether the more values of y are bigger than mu y or less. So it is relative variation of x and y with respect to their means. That is why it is called covariance between x and y. Is that clear?
Yes.
So what we can look at, we can have some simplified expressions also. If I expand it, I will get x y minus x mu y minus mu x y minus plus mu x mu y. That is expectation of x y minus mu x mu y minus mu x mu y plus mu x mu y. So this cancels out. So this we can also write as mu xy minus mu x mu y. Okay, the formula for the covariance: expectation of xy minus expectation of x into expectation of y. Is it clear? Let us look at the effect of independence also on this product moments. See, if I have, say, let random variables x and y be independent. Okay. Suppose they are continuous with densities f and fy respectively. Then let us consider, say, expectation of x to the power r, y to the power s. X to the power r, y to the power s, fxy dx dy. If they are independent, then it becomes fxx and fyy respectively. So I can split this joint integral as the product of the integrals which is nothing but expectation of x to the power r into expectation of y to the power s. What does it mean? It means the expectation of a product is equal to product of the expectations if the random variables are independent. Is it clear?
Yes, sir.
The similar proof you can write for the discrete case also. So I am not writing that thing because there the joint summation will become product of the individual summations. Okay. So in particular, if x and y are independent, then covariance between x and y, that will become 0, because it is expectation of xy minus expectation x into expectation of y. So if the random variables are independent, then expectation of x into y will become expectation of x into expectation of y, and the two terms will get cancelled out. So is that clear? So we also use notations. See, sigma x square as the variance of x, sigma y square as the variance of y, and sigma xy as the covariance between x and y. Okay. We define coefficient of correlation as, okay, the correlation between x and y. Okay. So I will use the notation rho xy, that is sigma xy divided by sigma x sigma y. That is the covariance divided by the standard deviations. That is defined as the coefficient of correlation between random variables x and y. Let us look at the interpretation of this, that what does it mean? What does it actually represent in terms of the numerical values of the random variables x and y? So we have the following theorem. For any jointly distributed random variables x and y, -1 is less than or equal to rho xy less than or equal to 1. Okay, it is always lies between 0 and 1, -1 and 1. So let me look at the proof of this. Okay. Let me define random variable u as a standardized form of x, that is, we subtract the mean and divide by the standard deviation. And v as the standardized form of the random variable y. Okay. Then first of all, let us look at the interpretation of all these quantities. So what is expectation of u? That will become 0. What will be expectation of v? That will become 0. What is expectation of u square? That is expectation of x minus mu x square by sigma x square. That will become 1. What is expectation of v square? That is expectation of y minus mu y square by sigma y square. That is again 1. And what will be expectation of u into v? That is expectation of x minus mu x into y minus mu y divided by sigma x sigma y. That is the correlation between x and y. Is this clear? If we use the random variables u and v, then these expressions are okay.
Yes, sir.
Now let us consider expectation of u minus v whole square greater than or equal to 0. See, u minus v whole square is a non-negative quantity, so its expectation will be non-negative. So this means expectation of u square plus expectation of v square minus twice expectation of uv is greater than or equal to 0. I have expanded u minus v whole square as u square plus v square minus twice uv, and expectation of u square and expectation of v square is 1. So this will become that 2 minus 2 expectation uv is greater than or equal to 0. It means expectation of uv is less than or equal to 1. Similarly, let us consider expectation of u plus v square is greater than or equal to 0. Okay, one I am considering expectation of u minus v square is greater than or equal to 0, and another one is expectation of u plus v square is greater than or equal to 0. So again this will imply that expectation of u square plus expectation of v square plus twice expectation of uv is greater than or equal to 0. And I substitute u, expectation of u square is 1 and expectation of v square is equal to 1. So that will give me expectation of uv greater than or equal to minus 1. And expectation of uv is nothing but covariance between correlation between x and y. So this means So this proves that the coefficient of correlation always lies between -1 and 1. So to get more clarity about the role of this coefficient of correlation, let us look at the extreme cases. Okay. One thing that we can see that if we have expectation of u minus v square is equal to 0, that will give me rho xy is equal to 1, isn't it? So, but what does this mean that u minus v whole square expectation is equal to 0? This implies that expectation of, see, a non-negative quantity, so you are integrating or summing over certain region, and a non-negative quantity summing or integrated over a region gives you 0. It means that that value itself should be completely 0. That value should be 0. So this means that probability that u is equal to v is 1. Now u is equal to v. What is u? U is x minus mu x by sigma x. What is v? V is y minus sigma y by y minus mu y by sigma y. It means that x and y are they have some sort of linear relationship, cy plus d, where c is positive. Okay. So we call it, then that means x and y are linearly related. Okay. That is x and y are perfectly, or you can just say linearly related in a positive direction. Okay, so rho xy is equal to 1. It is corresponding to a perfect positive linear relationship. Similarly, if you look at the left hand inequality, so when is expectation of u plus v square is equal to 0, that means rho xy is equal to -1. This means that probability that u is equal to minus v is equal to 1. Now, if you put minus sign there, it becomes x minus mu x is equal to sigma minus of sigma x by sigma y, and then of course some term is there. So it means that probability that x is equal to cy plus d, where c is a negative number, that is 1. That is x and y are linearly related okay in a negative direction. Okay, so this then gives you a proper interpretation of the coefficient of correlation, because from the extreme values we can make out that this is a measure of linear relationship. Okay. Thus rho xy is a measure of linear relationship between random variables x and y. And of course, you have one middle case, that if rho xy is equal to 0, we say that x and y are linearly uncorrelated. if x and y are independent, then rho xy is equal to 0. That is true because if x and y are independent, then covariance is 0, therefore correlation is also 0. But the converse is not true. I will give you one example of the converse here. Okay, let us take, say, x and y jointly distributed. Let us put, say, x here and y here, and suppose x is taking two values 0 and 1, y is taking three values -1, 0 and 1. Suppose this probability is 0, this is 1 by 3, this is 0, and suppose this is 1 by 3, this is 0, this is 1 by 3. Okay, so what are the marginal distributions of x? So you can sum here 1 by 3, 1 by 3, 1 by 3, and this is 1 by 3, and this is 2 by 3. So you can easily check here what is the expectation of x. Expectation of x will become 0 into 1 by 3 plus 1 into 2 by 3, that is 2 by 3. What is expectation of y? Expectation of y will become -1 into 1 by 3 plus 0 into 1 by 3 plus 1 into 1 by 3, that is 0. What is expectation of x into y? So expectation of x into y. So you look at all the combinations: 0 into -1 into 0 plus 0 into 0 into 1 by 3 plus 0 into 1 into 0 plus 1 into -1 into 1 by 3 plus 1 into 0 into 1 by 3 plus 1 into 1 into 1 by 3. This is 0, of course. This is 0. So this is, of course, then if you add up, this is again 0. So here mu xy is 0, then you are getting mu x mu y is also 0. So you are getting the coefficient of so covariance between xy is 0. This means rho xy is 0. But here you can see that the random variables are not independent, because if you multiply this 1 by 3 into 1 by 3, you don't get 1 by 9 here. If you multiply this 1 by 3 into 1 by 3, you don't get 1 by 9 here. So you can check here that the random variables are not independent, because the product of the marginals is not equal to the joint. Is it clear?
Yes, sir.
So I will stop today's class at this moment, and tomorrow we have the class test as I already announced, and that is based on the continuous distributions and the Poisson process. So that we will have, and in the next class I will continue bivariate normal distribution, and then the functions of the joint random variables and the sampling distributions. Okay.